So go on. Yeah, I can do, but I think we would be good. Someone come and check. Okay, but I will call you when you finish the
Okay, today what I would like to talk about is what's been called the credibility crisis in psychology. I mean, these issues are decades old, but the last 3 years have particularly highlighted some problems in the way we conduct science. The problems that may have gotten worse in roughly the last 5 years, and I want to, many of you know about that, but I'll just run through maybe a little bit of what you know, some things you might not know, and then argue that Bayes should be part of the solution to the problem. So, in doing that, by the way, I will mention some results, which I'm not especially part of the reproducibility project, but I found that the results from that really struck me and made me think we really have a problem. So that's why I want to tell you about those results as that project stands this year. It hasn't finished yet. Well, the problems go back a long way, and you probably, so this is some material that you'll generally know about, at least some of this. So there's a file draw problem, you know about, you get non-significant results, nobody publishes them, they get stuck in file draw, and so the published record becomes a biased record of what we should know, or how strong the evidence is for certain results. Now, the file draw problem is the problem of non-significant results being regarded as uninformative, and therefore being on the way somewhere out of sight. The opposite problem is even more pervasive, and that is when non-significant results are taken to be informative when they're not, or at least no demonstration is made that that non-significant result is actually informative. So I took, to demonstrate this, I took just at random a prestigious journal of Psychology General, just took an issue from it. In every article, bar one that used Bayes, but in 100% of the articles, a non-significant result was used to assert a null hypothesis. And it's used to assert a null hypothesis in order to draw theoretical conclusions. Now that's completely wrong. You all know that. And, well, you know that's wrong because if the key result had been non-significant, it wouldn't have been published, right? That was the previous problem. But now what happens, the converse problem is, when a key result is significant, you get a significant main effect. Well, the non-significant interaction is then interpreted willy-nilly as good enough evidence to assert the null hypothesis of no interaction. So, as long as there's a significant result in there, psychologists feel completely free to ad-lib interpret non-significance as evidence for the null hypothesis. One journal editor said to me, yeah, that's just bad journal editing. Doesn't happen under me. I didn't really believe him because every talk I go to, every article I read, pretty much has this problem. Once you look out for it, you'll see it everywhere. Now the problem isn't just a minor one. Consider life and death situations like a drug having side effects. So a drug company might say, this drug doesn't have side effects because they're non-significantly different from placebo. Well, that isn't evidence the drug doesn't have side effects. That's just non-significance. In fact, in this particular case, it was shown that this drug was declared to have no risk of increased suicide in children. It was later shown to have such a risk. So, when you use non-significance to say there is no effect, simply because there was non-significance there, that can be life and death, that can be a matter of human suffering. And where it's not a matter of life and death, it's a matter of theoretical development. And because, as I say, I see this in practically every article I read, every talk I go to, I think it's been an insidious corruption of the entire theoretical development of our field, and you're left wondering, what can you trust? So this is going to be part of the credibility crisis that I'm talking about. So, I mean, these issues are old, but it's the last 3 years that they've sort of come to the fore and hit consciousness. So one of the key papers was Simmons et al. 2011. They went through what you call analytic flexibility. So this is a term that's now come into everyday use amongst psychologists, analytic flexibility. And that's the notion that there are a whole range of ways of legitimately analysing your data. So that's why analytic flexibility doesn't seem like cheating, because if we give a data set, there's always another way you can analyse it. So they've got here controlling for gender or interaction of gender with treatment. Actually, this one is cheating. Addition of 10 more observations per cell. I'll get back to that one. So you run it, not quite significant, you run 10 more subjects. Well, unorthodoxy that is cheating. You have 2 dependent variables. Do you report both? Do you pick just one of them? Well, all of these things, I suppose it's not surprising that when you have this freedom to try out different things until you get a significant result, that bumps you up your type 1 error rate. I guess what was surprising is when you put these things together, you could get 60% of the time on the true null hypothesis, you get p less than 0.05. And what's disconcerting about that is this is just a tiny sample of ways in which we have analytic flexibility. How do we exclude outliers? Do we transform the data? Do we do a non-parametric test? Etc.
Or you don't.
Or you don't. And then this question, well, how prevalent are these practices? So John et al. Had this paper in 2012 where they asked researchers whether they engaged in these different practices. They also asked them to what extent do they think a researcher would report engaging in these practices if asked in this sort of survey. And that gives you a way of getting an estimate of the true prevalence as opposed to total prevalence. So you see some of the estimated prevalence is close to 100%. This is failing to report all dependent measures. Well, 78% of people say they've done that. True prevalence is probably close to 100%. And I'm not here moralising in the sense of holier than thou, because I also have failed to report all dependent measures. Collecting more data after seeing whether results were significant or not. Well, 72% of people say they've done that, and true prevalence is estimated close to 100%. And yes, I've bumped up data as well. Failing to report all conditions and so on. So you go through this. In terms of analytic flexibility, it's highly prevalent. So these processes by which type 1 error rate can be inflated to something uncomfortably close to 100% are actually widespread. So then the question is, does this make a difference? Can we detect the difference? Well, you might have seen the bump in the p-curve. So this is a plot of the distribution of p-values from JP General and some other journals. And you've got this little bump here. It's quite a nice smooth curve, except for just below 0.05. It suddenly becomes...
Just a chance.
Yes. Well, yes. So this is called p-phishing, or p-hacking. And clearly, what you do is, p is 0.07 or something, you think, well, surely this counts as an outlier, or you transform a little bit, you hunt around a bit, you get it just below 0.05, or you collect subjects until it's just below 0.05, you stop there.
Wouldn't you get that same effect just from the publication bias then?
A bump just below here.
Yeah. To some extent, in the sense that...
Yes.
So there are...
That is possible. I mean, any sort of bias that is specific to 0.05 could produce it. But given that we know that there are all these other biases going on, I personally suspect it's not just publication bias. Yes. Now, the other thing that's happened that's heightened the sense of credibility is the attempt to replicate results, and behavioural priming has been, well, the sort of the example that has really hit the scene. So these papers have come out just one after the other. When these papers first came out saying they failed to get behavioural priming, they tried to replicate Barge or someone who didn't get behavioural priming, I thought, well, okay, people fail to replicate. Effects sometimes don't replicate. But then it was just one paper after the other. Some of these papers, like this one, had 900 subjects in. The original paper was 50 subjects. Very high power replications. Nothing. Nothing. So just paper after paper, failing to get behavioural priming effects. So these are effects reported in popular science. They're all over the... any book in psychology that's in popular science, you get behavioural priming. They appear in newspapers and so on. But they don't replicate. Direct replications do not give you the effects. So that's extremely worrying. A systematic attempt to deal with this is the reproducibility project, which I think is an act of genius. The brainchild of Brian Nosek. What he decided to do, to have a look at how big is this problem generally, is take 3 high prestige journals, more or less randomly take 80 papers, 80 studies from the year 2008, and just crowdsource and say, who wants to try and directly replicate these studies? The procedure was that you should write down the exact method you plan to do. You should run it by the original authors. In most cases, the original authors said, yes, that's fine, that's exactly right, that's what you do, there's nothing else for me to say that you need to bear in mind. So you have that agreement before you get going. There might be several labs that are attempting a given replication of the study. You have to ensure that the power is high, ideally more than 95%, in fact the median power is 97%. So these are sensitive studies. And as of May 2014, 31 replications were completed of those 80. So now the question is, what is the reproducibility rate? So what proportion of these replications will be significant given the power of about 95%? So I don't know what your estimate is, somewhere between 0% and 100%. Now, sort of the limits we can put on that is if in those studies, in fact, H0 and null hypothesis was true in all cases, well, 5% will become significant at 5% level. So that would be the lower end, that would be a complete disaster. At the upper end, if all of the alternative hypotheses are true, well, with 95% power, you expect to get 95% significant results. So I don't know if anyone wants to guess. Okay, so this is it. It was 35%. So 11 out of the 31 replicated. This is a plot of the original p-value, and that's the replication p-value. So, you see here, even when the original p-value was 0.0000 something, sometimes replication p-value is way up here. If the original p-value was greater than 0.03, never replicated, which would be consistent with p-hacking, getting it just in there, and then satisfied. And just in case you're interested, this is the distribution for different journals. Science is particularly bad. JPLMC is not bad. I personally think that's because it's multi-experiment articles. That's what JP does. And it's when you get one-off experiments in a paper, you're going to most likely to fall foul of these problems. Because if you're going to have to replicate your effect several times and modify it in the process of theory development, you need an effect that replicates. So the move around about 5–10 years ago to go to one experiment in journals was probably a huge mistake. And especially emphasising sexiness. Just a one-off experiment that has a good headline probably really encouraged bad practice. The other thing over the last 5–10 years that probably really encouraged bad practice is performance management. So that if more or less every experiment you do has to get results, keep on the treadmill, to keep publishing, people are going to massage more.
I mean, at least until recently, JPSG was real different from JEP as far as being a multi-experiment thing. My girlfriend used to be like my editorial assistant, so I used to have to read a lot. And then
Right.
But I mean,
Depends which sections.
yeah.
In the third section, the personal and individual differences section, it's more usual to have single study papers. They're not large.
Is that new or
collaborations.
was that true in 08?
Yeah, it's been true for years.
Yeah.
So sections 1 and 2, social cognition and intergroup 1, has been a strong trend for some years, I would say a decade or more, for multi-study papers.
Right.
So it just depends on what they pick. I'm just saying JPSG has a worse percentage than
Yes,
science.
I don't follow that journal, but
Yeah.
yeah, it'd be interesting to know. I mean, obviously this is just a snapshot of 31 studies, and it's going to be interesting to see, for example, as well, not just this project, but hopefully these types of projects will continue, and we can track, like, is the last 5 years when performance management has increased, is that particularly bad compared to previously? My personal experience was, at least when I started a lecture in the 90s, was you run an experiment, get an effect, and play with it. Then when you're happy you got something, you write up the paper. Doesn't feel like that anymore. PhD students now feel that you need to publish X papers and feel this pressure. It wasn't like that when I was doing a PhD. I had one paper and my supervisor said he's a good chap and I got the job here.
That was a mistake.
Now this is interesting. This is a plot of the original effect size, expressed as R, and the replication effect size. Now let's say the original effect size is possibly biased by publication bias and other biases, but the replication effect size is unbiased, at least in the sense that no matter how big the effect was, it's going to be reported, right? There's no bias in the reporting of these effects. Apparently, when the people did the replications, it wasn't if they were biased against the effects. Brian Nosek said, he reported on this, that they did ask how strongly do you expect to get an effect. And most of the people who picked an experiment said, yeah, I think I'm going to get this effect, I think this is a nice effect, I'm going to get it. So there wasn't a bias in that sense. So, if we take this, our best guess anyways, this is relatively unbiased compared to this. What you see here is a fairly even scatter below the line of identity. What that means is your best guess of an effect size, if you read a published paper and there's an effect size, your best guess of the effect size is half of what it says. If there's an effect there at all, it's probably about half of what it says. So that would be something to bear in mind, for example, when you do power calculations or anything like that. So the upshot of that for me is there's a real problem. So it's not something we can just forget about and say those are cute arguments. It's a real problem. There's a genuine credibility crisis and something needs to be done. But I haven't come here to moan, and one reason why I'm in a way quite excited about the problem is there are now solutions that are happening. Things are changing. And these are changes that have been suggested for decades, but what's great to see is now they're happening. So, pre-registration. This only started about a year ago. Chris Chambers came here to talk, Cortex just started it, about pre-registration there. What happens there is, the idea is to change the incentive structure for research, because at the moment, you're incentivized to get significant results. In other words, you're incentivized to get a certain answer to a scientific question. But that must be completely wrong. The point of science isn't to find that answer. The point of science is to find whatever the answer is, right? So what you should be incentivized to do is good science, and then you've got to live with the answer. So what you do with pre-registration is the introduction and the method section are sent in, plus a complete protocol of your analysis. Of course, analyses are difficult things, so you might have to have a branching if-then structure. But you have to specify and think about that in advance. I'm on the editorial board of the pre-registered reports on Cortex. Well, it's amazing when you think about it, when you have to do it in advance, just how much you have to think about it and how difficult that is. But then the payoff is, let's say you've got a really good idea for an experiment. The idea is great, you can set up a rigorous experiment. Well then, you get acceptance for publication before the results are in. You're no longer at mercy of what the results are. It's going to be accepted. So then you get an unbiased record of the answers, what the data will tell you. So I think this is extremely important. And what's interesting, well, at about the same time as Cortex, so talking about a year ago, Perspectives in Psychological Science also set up pre-registered reports. Now there's a dozen journals doing that.
How popular is it? How many people are doing that?
We have in Cortex about a dozen papers going through the system and several gone through to completion. So there's a journal, Comprehensive Results in Social Psychology, just about to be launched, which will be only pre-registered, of course. The Royal Society is just setting up a journal. They'll have pre-registered reports. So when a prestigious institution like the Royal Society to cover all the areas of sciences does it, this is not just psychology. Yes?
But how well defined are the criteria for rejecting when you only have, because you lack the interpretation of the results, this interpretation of the results is very, very important
Yes.
as well.
So what happens is you get an in-principle acceptance at the first stage, so that, but typically this has to go back a few times because people don't quite specify fully the full analysis protocol, because we want to leave no wiggle room, no analytic flexibility. Everything's specified in advance. So that goes back and forth. Then you get in-principle acceptance, which means it's really highly likely to be accepted. It's not strictly guaranteed, because then there's another reviewing process when the results are in. You have to keep the same method section, the same introduction, so that's exactly the same. The results, you have to report the pre-specified results, but you're not restricted to them. So you can then have another section where you say, yes, but we poked around and found this and isn't that interesting. But there'll be two separate sections so that you can identify what was specified in advance and what came afterwards. And then the reviewers will say that they can comment on whether the discussion actually follows the results. But it's not going to be rejected, and they'll just go back and forth until people are happy that that's been brought into line. Yes, Chris.
Can I just quickly ask, from Cortex, what the methods are? Are these all behavioural ones, or is it neuropsychological?
No, we have fMRI. I mean, we've got an ERP one that's been accepted and is now. So the first stage has been accepted, and actually no, the collected data has come back again. That one's gone through completion. And an fMRI one has come and hasn't reached in principle acceptance at the first stage yet, but that's in process.
Are pilots still conducted in advance?
Yeah, no, pilots are really good, because I would think unless you did a pilot, you wouldn't really know how you're going to analyse it. So very typically you do a pilot, you can report that as well. So that is, as I say, that's gone from 2 journals a year ago to about a dozen journals now. So I find that really encouraging. This is a change that's I hope, set. Yes?
Do you have any idea whether in preclinical research there is any journal that does follow the same kind of, or is thinking
In clinical research? Preclinical.
Animal research.
One of the journals is an addiction journal that's doing it, but has addiction in the title, but I'm not sure if that was an animal journal or not. If you go to this website, it lists all the journals that have that have currently publicly declared their they do pre-registered reports, and there's a few more that haven't gone public that are coming through the system. So you can have a look at that. The other thing that's happening more is publication of direct replications in prestige journals. So that's very healthy as well. I mean, what you always taught scientific method is, I don't know where these numbers come from, but you hear numbers like, we never accept a scientific result until we replicate it 3 times. Because that's largely bollocks. It doesn't really work that way. But in any case, students are taught that the beauty of science is it's a self-correcting mechanism, right? But it's not self-correcting if you don't have direct replications. Because, and this is the point how Paschal makes very well, if all you had is conceptual replications, what happens is someone tries to conceptually replicate an effect. By conceptual replication, I mean you change the paradigm a bit. You explore if it's a bit more general. It doesn't replicate. So say, well, that was a fool. I shouldn't have changed it so much. But you don't change your confidence in the original effect. You run some more, but when it does replicate, you say, there you go, it generalises here, I'll publish that. So everybody's confidence in the field is constantly increasing with no negative feedback loop that's telling you there's nothing going on here. And maybe that's what happened in the behavioural crime literature. So I haven't myself submitted a pre-registered report, but in terms of my own work, I do have one experiment paper in Cortex, which I'm keeping in Macquarie, said, well, that's quite interesting, we're going to directly replicate it. So I'm all for that, and it doesn't, I mean, obviously I hope they do replicate it, but if they don't, I'll certainly link to their results because, and to their publication underneath my list of paper, because I would want people to know whether that effect replicates or not.
Do you know if research councils are getting on board with the scheme? I mean, I'm just thinking, writing a grant where I would suggest I want to replicate these studies and the likelihood of getting that.
Yeah, I don't know. I think it's percolating down into sort of popular research, into people's minds now. And so I think it could get a good reception now, in a way it wouldn't do just 1 year ago. Yes. Okay, and then the other thing that's happening, again, this is something Brian Nosek has done, is he set up the open science framework. If you go to this site here, what you can do is you can put up there, you can link with a group of researchers, say, working on a common project, or if it's just you, it's just you. Then you put up all your materials, your programs, your results, your data. Then, at a first pass, what you have then is an enduring record of everything that happened. So that, say, a PhD student leaves, you've got the materials, you've got the data, everything is up there. Now, there's a little button which roughly says go public. Now, anytime you want, you can click that button. You don't have to do that, but if you want, click that button.
Can you unclick it?
Sorry?
Is it a one-way street? You unclick it?
Yeah, I actually haven't clicked it yet, so I'm not sure. Oh, we did click it. Yes, we do have. I now have. I'm pleased to say I'm not completely hypocritical here. Ryan and I have put up some. We put up one of our experiments up here. We've put the complete data set up there. So now anybody can come, look at our data, and say no, they can criticise it. It's transparent. It's open. Now, this has to be the direction science goes, maximum transparency. It's then when you have your, ideally the raw data, the original data, you have the rawest form up there, your analysis protocols as a statistical script, your programs, everything is up there, and it's completely transparent and public, and anybody can spot flaws there. And if you have been p-hacking, someone else can say, well, I analysed that 11 different ways and it only comes out your way once. So that's got to be part of the solution as well, transparency. There are some journals which demand it, and that's increasing. So POS now wants your data online in a public space. It isn't just your web space, which is transient potentially, but an enduring public location, like on the Open Science Frame. The Royal Societies in the journal will demand that as well. So these I think are very healthy. The one I want to concentrate on now is Bayes, and Bayes is making a real difference. I mean, people have been arguing about Bayes and saying everyone should be Bayesian decades ago. Now, the changes that have been happening in terms of the acceptance of Bayes is also startling to me in the way that these other things are. So, for example, the APS says, just 3 months ago they said, you can have a results section that's purely Bayesian, no significance testing, and that's perfectly acceptable in our journals. Which rather surprised me, because I haven't been going around saying that. I'm saying, no, keep your normal significance tests, add in the Bayes so people learn to read both of them together and compare them. Addiction, the journal, which Robert West is the editor of, is just writing an editorial suggesting that any non-significant result published in it should be accompanied by Bayesian analysis. I'm on a number of journals, including Cortex, specifically as a Bayesian to encourage people to use Bayes and to guide authors in Bayesian analyses. So the same sense here of it's building up and we're on the cusp of a change is also here for Bayes. So what I want to say is why I think Bayes is part of the answer. So Bayes helps for two reasons. One is Bayes factors are symmetric measures of evidence for the alternative hypothesis versus the null hypothesis. The other thing they do is they relate theory precisely to the data relevant to it. So I want to go through what that means and why that's important. What these things mean is you can get support for the null hypothesis, which has been missing in our statistical techniques. They're insensitive to stop and go, so that helps with a certain aspect of p-hacking. They're independent of the timing of data relative to theorizing, so that helps with a certain sort of cheating, and they're independent of the number of comparisons. So, in general, what we'd like to know is when we have, well, we normally set up the world so that there's a null hypothesis and there's alternative hypothesis. It doesn't have to be that way. Let me just stick with that because that's something we've inherited from orthodox statistics and we seem to naturally think about things that way. So given that we have two models of the world, there's actually three conclusions we could come to. We could say, actually, we've got good evidence for this model. We've got good evidence for the other, or the evidence isn't discriminating. There's no evidence to speak of either way. We want to make a three-way distinction. P-values make a two-way distinction. They don't even make that very well. But to the extent that they do make a distinction, they can only make a two-way distinction. If P is less than 0.05, in some weak sense, there's evidence for the alternative. But if it's non-significant, no discrimination is made between these two states of affairs. No matter what the p-value, no distinction is made between the spots. A p-value of 0.9 doesn't mean good evidence for the null hypothesis. It might mean your data are completely insensitive. It really doesn't mean that in any way. No distinction is made within this box. You can't say because my p-value is 0.9, that's good evidence for the null hypothesis. But a Bayes factor makes a three-way distinction. So a Bayes factor is a number. If it's quite small, less than a third, then there's substantial evidence for H naught. If it's more than 3, then there's substantial evidence for H1. And if it's somewhere around 1, then there's no evidence to speak of. So we get the three-way distinction that we wanted all along. Now what that means is, because it's perfectly symmetric, you can publish evidence for H naught, just as much as you can publish evidence for H1. They're just two models as far as the base factor is concerned. But it's the only way you can do that. So, what that means is it will solve the problem of publishing null results, the file draw problem, in the sense that when you have good evidence for H0, well, you can publish that. There's no reason to put that in the file draw. Furthermore, in experiments where they do have a key result significant, and people have been using null results willy-nilly, well, they'll only use them once we're accustomed to this way of thinking. They'll only use them when actually there is evidence for H0. Now, there's another thing that follows. You can p-efficient p-hack, you can b-hack as well. In other words, you can play around with your data and you can push a base factor more one way than another. Maybe by getting rid of outliers or not getting rid of outliers, by transforming, not transforming, and so on. There's some ways of massaging your data going to make it look more evidential than others, and there's not a way around that. But that problem is mitigated because the evidence can go both ways. And you can also run subjects until the evidence is strong enough, which you couldn't do with orthodox statistics. With orthodox statistics, you could only hack and fish in one direction, right? So there's an inherent bias in the procedure. Another thing is replications can be properly evaluated. I looked at some of the replications on the reproducibility project, some of them very high powered. They get a non-significant result. You might think, well, this is a high powered null result, that will show the evidence for the null hypothesis. No, not necessarily. Power is extremely problematic as a measure of sensitivity because you don't use the actual data you've got to assess the sensitivity of those data in terms of what they're saying evidentially. So you're not using the most informative aspect of your experiment, namely the data, to draw a conclusion about its sensitivity, which is utter madness. So just because you have a high-powered experiment doesn't mean actually you have a sensitive discriminating experiment. You have to use the data that you have to determine that, and so you need to use base factors. So you can properly evaluate replications when you have base factors in a way you can't do with orthodoxy. So, to summarize what I said so far, base factors will seriously help the first two problems I started with, the file draw problem and the problem of using non-significance to assert null hypotheses. So that is a big help in itself. Now, base factor, this is a base factor here. This is just a rearrangement of the axioms of probability. All of this just follows from a few lines of derivation from the axioms of probability. So what it means is that if you're willing to treat strength of belief, at least in some normative, idealistic sense, as following the axioms of probability, then the base factor tells you how much you should change your beliefs in light of the data. Now, if you think how much you should change your beliefs in the light of data is a good measure of strength of evidence, then normatively the base factor is the right measure of strength of evidence. Furthermore, since it follows from the axioms of probability, the strength of evidence only depends on this term here and on nothing else. So it only depends on how likely the data were given each hypothesis. That's all strength of evidence depends on, nothing else. So in particular, it doesn't depend on your stopping rule, because the stopping rule doesn't enter into those equations. Those equations were followed from the axioms of probability, so I tend to think that's a pretty good conclusion up there, that the stopping rule should be inferentially irrelevant to your conclusions if you're drawing conclusions correctly. But now, the stopping rule in the orthodox approach is extremely important. What stopping rule means is you need to say in advance when will you stop collecting the data, and then when those conditions are met, you stop, and that's it. And then you have whatever you have, and you can do no more. Now how that works out normally is you plan in advance a certain number of subjects, you run that precise number, and then you stop, and that's it. Now if you just miss out on the significant result, you're not allowed to just run 10 more subjects and test again. You're not allowed to run until you get a significant result. The reason for that is, as I pointed out, P is asymmetric. It can only evidentially go in one direction. So now what happens if the null hypothesis is true? Your p-value does a random walk in the range 0 to 1 as you collect more subjects. What that means is, because it's walking down randomly, sooner or later it will go into, it'll take on any value. You just have to wait long enough. So, sooner or later, your p-value is guaranteed to be less than 0.05 if you just wait long enough. So you're guaranteed to get a significant result if you just keep on running and testing until you get a significant result. Therefore, such significant results must be evidentially useless. Now, a base factor, by contrast, is symmetric. It's driven in opposite directions, depending on which of the two theories is true or not true. If the alternative, at least the way around I programmed it on the calculator, if the alternative is true, B is driven to infinity. If H naught is true, B is driven to 0. It's driven in opposite directions. And so, and that's sort of an intuitive way of saying, but there's more rigorous proof, that the stopping rule doesn't matter for the base factor. So what you can do is you can decide, I'm going to run until the base factor discriminates one way or the other between H1 and H0. I'll stop when my base factor is either more than 3 or less than a third. Then you've got the discrimination you needed with the minimal number of subjects, so you have optimal efficiency and no cheating. Now this leads to a moral paradox with significance testing. If you, let's say you have P of 0.07 after running the planned number of subjects. If you run more and report significance of 5%, you cheated. We all do it, you cheated. If you don't run more and bin the results, you waste the taxpayers' money. And you've wasted data that's relevant to drawing a conclusion. And that's wrong. You're damned whatever you do. It's only Bayes that allows you to stand outside of that circle of damnation. I mean, you asked me when I said this in the lecture, well, why don't you just publish the P equals 0.07? Well, of course you can't publish it, but even if you could publish it, you just push the problem back. So now what do you do with that? What conclusion do you draw from it? If someone now uses that to collect more data, and they combine it with that data meta-analytically, you cheated. Yes?
I'm missing something here, Zoltan. So when do you know that you've got a significant result with the Bayesian approach?
Well, don't use the word significance, but it's, well, the base factor is a continuous degree of evidence, where 1 means it doesn't discriminate, because you wouldn't change your prior odds at all with 1. So the data not evidentially either way. And either the bigger it is or the smaller it is, the stronger the evidence is one way or the other. So now, because we love conventions, arbitrary conventions, we can come up with some conventions. You want conventions? So, in fact, Harold Jeffreys, who developed base factors, who was a Cambridge astronomist and geologist and statistician, in the 1930s published the first public statement of base factors. He suggested it's 3 1/3. Now, having played with it, I found that to be a really good choice in the sense that when you run an experiment that's significant at 5% level, and you get an effect size that's about what you expected, the base factor will be about 3. In other words, it matches the standards of evidence we're used to having as scientists. That's not a necessary correspondence between significance and Bayes, otherwise it wouldn't add anything. But it's when you get the mean effect is about what you expected. And so it's about what your H1 says it should be, and it's significant, 5%. Then the base factor is about 3. So I thought that was a really good choice. So then that by symmetry gives us 1/3 or less for the same standard of evidence with the null hypothesis. So what you do is you can then run until the base factor is more than 3 or less than 30. So you don't know which way it's going to go. It might tell you you're getting better evidence for H0 or better evidence for H1. You don't know that, but you can run until it goes either way.
To what extent would you get the same effect if you did 2 experiments, one where H0 was treated as H1, and you worked in terms of 2 p-values? Wouldn't that just come out the same?
A p-value, it doesn't come out. First of all, the p-value has to be a point hypothesis. It's got a reference to a point. One of the good things about Bayes is our H1 isn't necessarily a point hypothesis. So we can set up models that you can't set up in.
But you just made a point, didn't you? You just said this relates to the 0.5 level.
Yes. So in other words, no, this is a matter of, this isn't a mathematical proof. In fact, you can prove the very opposite, that in general, for any significance level, that could be evidence for the null hypothesis. That just depends on how you set up the models. What I'm saying is, I've gone over hundreds of cases in psychology where I've thought about realistic base factors and realistic specifications of the psychological theories in that scientific context. And it so happens, roughly speaking, the base factor of 3, pragmatically, practically, is a pretty good match to the significance of 5%. So the base factor deals with the problem, and this is a real problem, optional stopping. I mean, what do you do when you get p equals 0.07? I mean, this is a real practical problem that base factors solve. Now, on orthodoxy, it matters whether you have a planned or post-hoc comparison. In fact, orthodox stats books have huge chapters on all different sorts of post-hoc tests you do in different situations. So predictions made in advance rather than before looking at the data treated differently. But the base factor doesn't have time in there, and that follows from the axioms of probability. So therefore, time can't actually be something that's inferentially relevant. Now, you might say to me that, hang on a minute, surely you've had the experience of kind of reading the paper. You come down to the predictions at the end of the introduction, and you say, I know before I even looked at the results, the only reason they made those predictions is because that's the way the results were, right? And you feel cheated. You say, this is sloppy and horrible and misleading. Those aren't predictions, even though they're put forward as such. So surely it is important. Because you're saying these are post hoc. These are obviously post hoc statements of the results just because that's what the results were. But hang on a minute, if you could spot that by reading the introduction, that means the problem is in the very statement of the theory and the predictions. Because you don't actually know what the timing of the events were. What it means is those predictions didn't follow simply from some elegant theory, and that's what you're spotting. And that's what the problem is, and that's the real problem. You see? So, time isn't really in some intrinsic sense, predicting in advance in some intrinsic sense isn't really what matters. But it's a really good proxy, it's a really good correlate, because if you do predict in advance, you probably did make the simplest predictions you can from some elegant theory. And if once you have collected data, a horrible set of predictions that don't really follow from any nice theory, well, that probably was post hoc, right? So planned versus post hoc is sort of pragmatically useful, but it's not intrinsically or essentially important to scientific inference. So that's what I think at the fundamental philosophy of science level, at least that's what Bayes says at the fundamental philosophy of science level, and I agree. But there is more to say about this, because what did I just say about pre-registered reports and how great they are, right? Exactly. And this is my answer. As I said, Bayes is still susceptible to analytic flexibility. It's still susceptible to, did you exclude those outliers or not? Did you use 2 standard deviations, 3 standard deviations, or something more complicated? Did you transform? How did you combine those dependent variables? And that's why registered reports is still a good idea. Now, to illustrate this, Joshua Carr had a look at commonly used decisions, analytic decisions in fMRI. He put them all together, took a single set of data, and all those different decisions produced 35,000 rather different significance maps. So what that means is there's a lot of analytic flexibility. You could say, I'll have that one because that fits my theory. So now, if you specify analysis in advance, let's say 90% of those maps tend to favour one sort of particular outcome, like a certain area being involved rather than not involved. Then, when you do specify in advance, you're 90% likely to choose an analysis that reflects what the data say by and large. That's why I think pre-registered reports would be terribly important for big data sets like fMRI, EEGs, and so on. So that's not contradicting what I said about Bayes, because what we'd like to, what we want to know is what are the data, what's important to us is what are the data saying. So here, for example, it's going to happen 10% of the time when you do this specifying in advance that you pick the analysis that doesn't actually represent what the data are saying by and large. So let's say you pre-specify an analysis, and it turns out to be the one analysis that gives you a certain result, and all the others don't. It's just like it's going to happen sometimes when you do pre-registered reports. So what was important was not that you specified it in advance. That was just a hack, a shortcut, a pragmatic rule, proxy to help us. If you did all those analyses on the data and you found that 90% of them pointed one way, it wouldn't matter what you specified in advance. You know what the data on balance say, and that's what's important. So what is always important is the relation of data to theory, and that depends only on the data and the theory. We might take some shortcuts like specifying things in advance, because that's going to just help us by not having to do 35,000 different analyses. So that's why it's a good thing. So now I'm going to go on to another slightly subtle point. On the orthodox approach, you must correct for how many tests you conduct in total. For example, as you can see myself over there, if you do 100 correlations and 4 were just significant, you would say, well, yes, I expect 5 to be significant by chance that I'm not going to interpret these correlations further. You do a correction for multiple testing. Now, with the Bayes factor, that Bayes factor didn't say anything about the other tests you did, when I derived them. All that was important was how well the data would predict the Bayes hypothesis, not how many other tests you did. So you don't correct multiple comparisons in Bayes.
So actually, if you have an hypothesis, then you're running planned statistics, so you should correct it.
Yes, although what would happen is, let's say you've got 10 hypotheses.
But that's another issue.
So what you can get away with in orthodox statistics, you say I've got 1 planned, or maybe 2. As soon as you say you've got 3 or 4, the reviewers aren't going to have it, are they? But maybe I'll do 3 or 4 hypotheses. So let's have a concrete example. Let's say Smith, let's say Smith et al. Looking at time to close a sale, and by close a sale I mean you come through to agreement and you've sold your goods. It was 15 seconds faster if the client sat in a soft rather than a hard chair. So that's in the published literature, there's the same. So you follow that up and you say, I know what. So that was soft versus hard. That's going to prime how hard you are as a negotiator. I'm going to prime close it. So hopefully the deal will be closed sooner if I can prime closing in some way. So you run an experiment where you talk about Sunday closing and see if the deal closes faster. Maybe you run a bunch of experiments like that. In the 6th experiment, you make funny closing actions with your hand as you're talking. And it so happens that in the first 5 experiments, not significant. Maybe average effect size 0. But in the 6th one, it's significant with T2. Furthermore, based on the principles of calculating base factors, I've already publicly stated I can apply in this case, you get a base factor bigger than 3 given these data and that are studied. So you say, there's evidence for making money and gestures helps close the same. You say, hang on a minute, there were 6 experiments. 6th one happened to get as an orthodox person, I'm going to correct. I'm going to say you need your p less than 0.05 divided by 6. In other words, you need p less than 0.008 before I'm willing to count against it if there's anything going on. Right? Well, but what about Bayes? Because in Bayes I said you don't correct for multiple comparisons, so isn't that a problem? So the basic answer is in Bayes, as for everything, you must use all data that's relevant to a hypothesis. It's relevant to a theory. You're not allowed to cherry pick. That's the important point. Now here, we're interested in, there's sort of a superordinate hypothesis, a superordinate theory that priming and closing in some way will speed up. Behavioral priming and closing will speed up when the deal is sealed. Now, given that the authors tried these 6 methods, they must have thought all of these methods were good attempts at testing, were plausible instantiations of that particular general theory. So what we can do is we can test how well the data support the superordinate theory that priming, behavioral priming and closing speeds up deals. So I've just gone through, let's say the mean priming for the other studies is 0. That's just for simplicity. So then it follows from there what the mean priming for all the studies together is. Right? I've assumed all studies have identical standard deviations in subjects. Well, then I can work out the standard error for that. So then I can work out the base factor, it just sort of follows for all the studies together, and that comes out to be 0.3. Now what that's saying is you have strong evidence for the null hypothesis and against superordinate theory. So what I would say is Bayesian, what this is telling you is the general theory that you're interested in and started with, you have substantial evidence against that for the null hypothesis. You also, as it happens, do have strong evidence for a particular variant of that theory. But now, the question is then, are you interested in the general theory? And what status do those particular variants of that theory have? If all those variants are to you, given background knowledge, just as good instantiations, there's nothing to do between them, then we'll just go with the evidence for the general theory and say the evidence counts against it. At the very least what you can do is collect more data until the evidence not only supports the specific theory that making funny closing hand motions closes the deal, but also, because if you collect enough evidence by bumping up this one, it will come out overall on a meta-analytic case as well. So the Bayesian answer is somewhat subtle, but I think it tells you what the data are actually saying. They're counting against the general theory, and they happen to count for one of the specific variants. And that's just the way it is. What you make of that is a scientific, not a statistical matter. Yes?
I still can't see why that's different from the p-values that you've shown. If you've got 5 other non-significant effects.
Yeah, no, you could do this in some sense. The same logic you could carry through that I've done here with the meta-analysis. You could do with the p-values. The thing is, what Bayes forces you to do is you always must consider your theory and what data are relevant to the theory. The p-value doesn't consider that because when you do corrections for multiple testing, what counts as a family, in other words, the number of tests that you do that you're correcting for, has nothing to do with theory necessarily. In fact, statistics will tell you it's to do with the degrees of freedom of some omnibus test. So, in other words, that means a particular comparison I have is being affected by data that's not relevant to that theory. It could be affected by data, by some tests and comparisons my research assistant does I don't even know about, but I should still correct for. For Bayes, the only thing that matters is the data, is the theory, the data relevant to that theory, and it forces you to think in just those terms. Whereas you have a arbitrariness in orthodox statistics where you don't have to think about that.
Is that arbitrariness still there in meta-analysis? And there are 2 or 3 of us in this room that have published meta-analyses, and we were perhaps under the misapprehension that because a properly done meta-analysis does include both non-significant and significant results, and I know it's still vulnerable to the file draw problem, but if you work hard enough and get all that gradage and so on, isn't that some safeguard? You know, if you can get 50 studies that have looked at something and then you can arrive at an average size and all that sort of stuff?
Meta-analysis is, I think it's a great thing, but similar sorts of problems can recur with a meta-analysis. So you do your meta-analysis and you get a non-significant result. What do you conclude from that? Well, then you need Bayes. But you can do a Bayes on the meta-analysis, it's very simple. You've got your meta-analytic mean and your meta-analytic standard error. You can use my calculator and see what that non-significant result means. And that's, in essence, what I've done here.
One of the issues is what exactly parametric statistics is for, because it's been developed not for science, technology. The student was working for a brewing company. So they were not testing an hypothesis, they were just testing. It was an efficient expedition. So most of statistical tests are, especially when you find the Taliban of statistics in one of the among your referees, right? So the statistics just conceived to correct for efficient strategy. So you correct 100 comparison, for example, you want to correct. But if you have really an hypothesis, then you should really have a statistical testing. So I'm going back to what you said about how we can correct. One way to correct really is to be very strict in the hypothesis being tested, which is not the case, even in major journal.
Yes.
The person screen for the hypothesis being tested is very loose.
Yes. I agree with you completely. Orthodox statistics is all about controlling error rates, which applies really well to the production line of a factory. How many defects are there? What we want to know as scientists is strength of evidence, the data bear on particular theories to help us in the process of theory testing, because that is what science is. You can get an approximation to that with orthodox statistics, but because it's just an approximation, it's let us get away with a lot of sloppiness in that way, and Bayes will force us to be better theory testers. That's not what I think. Yes. Yes.
So I was thinking about what's actually happening here if you run 6 studies. So you have your Bayes factor, but you also have the fact that we're considering the odds of the alternative hypothesis and the odds of the null. That's another term in the greater equation of the.
In fact, there's several ways of doing that.
No, I'm just curious whether there's another way of thinking about it, which is that after I've run 5 studies, I really shouldn't be treating them as equally likely anymore. So that perhaps that previous evidence should have told me that I need a much more compelling effect in the 6th study to overturn what I should have learned from the first 5.
Yes.
Yeah. So instead of like the way you did, just chuck it all in and say, okay, well now the Bayes factor is lower. Actually, my standard of evidence should have been much higher.
Yes. In fact, there is a Bayesian way of doing that.
Yeah. So I was thinking that's maybe more a more intuitive way of thinking about it.
Yes. See, what I do when I do Bayes is this is the Bayesian equation.
You should be changing your files.
Times by the Bayes factor, you get your posterior odds. What I do is I strip away your priors, posteriors, and I just do that. So I'm taking just a part of the Bayesian apparatus. But what you can do is you can take the full apparatus. And then you can use your previous studies to change your prior odds, that's right. And if you read John Krushke's book, for example, he tells you just how to do that. And that addresses the multiple comparison problem in a slightly different way, as you just mentioned. And when you put it through his equations, put it through his program, if you had a bunch of studies that were non-significant or the means were very, very close together, that changes the prior expectations for all the studies, so that you then need stronger evidence for any one of them to show that there is an effect there. That's exactly right. That's exactly what he does. I do something a bit simpler. I see what I can do just with the Bayes factor.
Trying to think about how you would.
That's exactly right.
You'd really be banging your head against the wall the 6th time if you've already had 5 go wrong. Like, get another theory.
Yes. Okay, so the things I've gone through are stopping rule, the pre versus planned, and the number of comparisons. What all of those things mean is for orthodoxy, you can have two people who have the same data, the same theories, but they come to opposite conclusions. And that would happen, for example, if just imagine you've got two people working on a study. They're collecting data, but they happen to have different stopping rules applied. So one of them thought he would run for 30 subjects, test. If it wasn't significant, he would run 10 more. Now that's a perfectly good stopping rule, but you have to control for the fact that you're testing twice. And what that means is, in that case, fairly simple. It comes out to pretty much at each point you need to test at 0.025 in order to have an overall 5% error rate for your decision procedure. So one person is building the stopping rule where you're testing twice. The other person just plans to run 40 subjects and look at it at the end. Now, as it happens, the data was non-significant at 30 subjects. So they both happily carried on running without realising there was a potential conflict there. Stopped at 40 subjects. I hope you're with me with this. It comes out as, say, 0.04. So one researcher says it's significant, the other says it's non-significant. So you have the same data, same theories, different conclusions. And what does it depend? What do the conclusions depend on in orthodoxy? They depend on what was going on in the people's minds. It depends on when would they stopped. Would the first researcher have stopped at 30 if it had been significant then, even though it wasn't? Well, that might depend on whether he could have convinced the other researcher to also stop then. And that might depend on who's got the best kung fu. And that would be mathematically the correct conclusion for the orthodox statistician. Yes?
But isn't it true that you correct for the family-wise error rate when you have multiple independent tests? And
or dependent, you could have tests which the outcomes are correlated, you can still correct. And the corrections can be somewhat different in those two cases.
Okay. Because in your example where you have you stop halfway through, you do one test, and then you carry on. They are, the second test would be dependent. Well, it's really correlated with the first.
Yes, that's right. And there are specific, I can give you a reference, there are specific procedures for doing that. It happens to be fairly simple in this case where you're just stopping twice. It's pretty close to 0.025. That implied I was just doing a Bonferroni. In fact, it's a bit more complicated than that. And there are, if anyone's interested, I can point you to programs that will give you proper decision rules for multiple testing.
But you would have to, I mean, if the tests are correlated, if the data, you would have to kind of...
You have to take that into account, yes. Yes, that's right. So, orthodoxy depends on subjective things, like the intentions in researchers' heads about when they would stop. Furthermore, it depends on those intentions even if the researcher themselves doesn't know what they... It can depend on things the researcher themselves doesn't even know about themselves, because what it depends on what they would have really done in certain situations. It depends on a whole bunch of counterfactuals that might in fact be unknowable. And certainly when we look at someone else's research, we could have access to all the data, all the relevant theories, but not know what was going on in their head, and therefore not know how we should analyse it. So, but because it depends on things, like what's going on in your head, like when did you think of something? Did you think of that theory before you collected data or afterwards? Wasn't there an inkling of it in your head before you? You know, it was related to that thing you were talking about with Joe, wasn't it? It's utterly subjective. So orthodoxy leads you in a very subjective position where, of course, you can cheat because no one knows what the right answers are for those cases anyway. Pre-registered reports helps because you declare it in advance and then you've got to stick with that. But in general, these depends on a bunch of things that can be unknowable, and in any case should be inferentially irrelevant, because surely what's important is just the data and the theories, and that's all that data depends on. So here's some practical conclusions from all that. when asserting a point null hypothesis, so check in a paper whenever you say there was no interaction. You just made a claim that could be interpreted about the population, that is highly misleading, unless you know you've got evidence for it. You can say there was no significant interaction, that's just a statement of fact about the way the results came out. If you say there was no interaction, you have to do a Bayes factor before you declare that. If you say the effect was the same for the men and the women, well, you just made a claim about a null hypothesis, you better have done a Bayes factor to support that. If you do get a p-value of 0.07 and decide to top up, thereafter you have to do Bayesian statistics. It's no longer valid because you had a stopping rule up until that point like that, and you weren't. You could say, I'm now going to do the correction. No, it's too late. Unless you plan the correction in advance, it doesn't count from an orthodox point of view. So, if you run the number of subjects you plan, p is 0.07, you want to publish that, you better be a Bayesian. You need to do a Bayes factor on that. Then it's okay. Consider all data relevant to the theory, and only those data. Don't correct for other tests that weren't relevant to that theory. But you must use all the data that are relevant to the theory that you're scientifically interested in. So orthodox statistics has a tendency to make you think you can cherry pick, because part of you can believe that a non-significant result is non-evidential. Therefore you can ignore it. But this is evidential and scientific because it's significant, so I'll take out. Well, that's not true. All the data that's relevant to the theory should be taken on board and used maybe meta-analytically to evaluate the theory. Now, I think things are changing, and that's great to see, and maybe in 100 years' time, people are going to look back on how we're doing science up to now and shake their heads in the same way that when we look back 100 years, we think those poor primitive sods. But I think the credibility crisis may have been the medicine that we needed to spur us on and say, yes, we really need to do something, and now all these changes are happening. Right, thanks very much.
You said that 0.3 was a highly significant null hypothesis.
That's what was
Bayes
factor. A Bayes factor less than a third is substantial support for null hypothesis.
Would that increase in significance approaching zero, or is it just...
Yes. No, and the closer the Bayes factor gets to zero, the stronger is the evidence. It's a continuous measure of evidence. Yes. So if you're not happy with 3 1/3, you might say, I want to do 10%. So the evidence is really strong because it's maybe a particularly controversial. Yeah.
So if you don't just use Bayes to try and sort out your people with 7 and add some more subjects, and you start off, I'm going to do basic statistics from the beginning, and so you just add subjects until you get to 0.3 or
that's what I recommend.
What's the kind of minimum N that you come across through experiments?
There is no minimum.
Because you can't do it with 1, 2, 3. How many?
Well, let's say it's a t-test situation. You need at least 2, so you've got a measure of variance. And you need the same. You need to estimate the standard error and the mean difference. So that means at least 2. Now, Bayes factor makes assumptions about distributions. I mean, you can use any distribution, please. The Bayes factor is a completely general principle. But, say, the Bayes factor calculator I put up there assumes normal distributions. And you could be happier that you had satisfied those assumptions if you've run more subjects. So that might be reason to run more subjects. If you already knew this was a situation from past studies where the data's pretty normal, then just run until it's more imperialist.
So would you stop at 2?
2 subjects.
Yeah. If
the Bayes factor came out that way. This is a good question. I mean, you could decide.
I'm talking just from the perspective of doing animal experiments.
Yeah.
And there's a big thing on if you go to the project license training stuff about how just ethically you have to use the minimum number of subjects you possibly can to do an experiment. Now, Bayes is one way where you can do that, and you can say, I'm doing it and every animal's useful because I'm either going to go one way. Well, I guess when do you give up in the middle is the other point. When do you give up and say you've got no evidence either way?
You might just say I'm not going to kill any more animals.
Yeah. So, but for that, they might say, okay, you have to stop at 2 if that's the point when you've determined your conclusion. But that seems.
Well, no, but remember with the base factor, you don't have to have a set stop control. So you can say I'll run until 3.
But if you said that when I hit 3 or a third, I'm going to stop.
That would be, then you do have, the evidence would be what it states, assuming the assumptions are satisfied. So you just have to ask, is 2 subjects enough? You'd be happy about that. And that would be the minimum number of subjects to get that evidence. But it would be, I think for animal research it would be perfect because you would be getting the smallest number of subjects you need to make a discriminating result. And even if you said, and I have to stop at 100, because I just can't kill anymore, that would be unethical, at least you would know that it's non-discriminating. Whereas with orthodox statistics, you probably say it's non-significant and counts against the theory that it did the difference. Whereas the Bayesian analysis would tell you, no, you can't conclude that yet. It doesn't count against the theory.
Is there an issue about having to specify HI and H1 in calculating Bayesian studies? I remember a long time ago, there was a paper by Paul Neal, which contrasted natural sciences where theories have specific point predictions, and you test your data against the point predictions of the theory. Whereas in psychology, we have the null hypothesis, which is a point 0, and everything else, in a sense, is lumped in as H1. Even though, as Neil went on to say, it's probably the case that 0 is always false, that any change in stimulus conditions is going to have some effect. And consequently, whether or not the result is significant is simply a matter of statistical power. If you've got enough subjects, tight enough control, you'll get a non-zero result. And then that leads on to questions about, well, actually, the null hypothesis shouldn't be specifically 0, but it should be some null range. And likewise, for the alternative hypothesis, it shouldn't be anything which is non-zero, but should be some, more specific value. But of course, that's where we then find that our theories aren't very able to tell us what their specific values are.
I mean, that's when I first got into this, that was sort of the sticking point, how do you specify H1? The more I thought about it, the more I realised there are solutions to that. So my papers describe actually how we have more information than we normally think about what our H1 is and the limits on it and the likely values on it. So I give some rules of thumb and heuristics to think about in my papers. As far as H1 is concerned, my calculator, you could specify an H1 that was not just a point value. It was a range.
But this is different investors. So going back to your kind of your priming study where you've got soft and hard chairs, I mean, how many seconds difference would you expect? I mean, you might say, well, I think it's going to be at least 10 seconds and anything less.
That's why
and somebody else would say, well, anything bigger than a second. And so we're going to come up with really different basis factors because we've
got different models. You're comparing different models, so of course you get different answers compared to different models. So
but the number of models then are infinite, aren't they?
Yes, that's right. Okay. But what we can do is, I mean, in that example, I said there was this previous study that we think they've got a 15 millisecond effect, and we think it was a paid priming study, and whatever mechanism was working there, it's roughly the same mechanism working here. As long as you're prepared to say that and to think that helps fix our rough estimate, it doesn't have to be exactly the same, as long as it's roughly in the neighbourhood of that previous study, then we've got enough information to get going. And I think H0 is probably truer than Miel implied, in that, yes, literally it must be a region, not literally point value, but if you put in my calculator for a reasonable region for H0, relative to the size of the standard errors that we have in our experiments, would make no difference to the conclusions that we get. An example would be, I mentioned that Barge study, which was about holding a hot cup of coffee versus a cold cup of coffee, and about trying to warm to someone else. Someone trying to replicate with 900 subjects doesn't get a significant result. And then there was an ESP study by that guy at Goldsmiths, Chris French. It was an online study with around about 40,000 subjects, and with a null value of 0.5, 50% performance. The confidence interval was something like 0.4997 to 0.501. I think when you counterbalance things quite well, actually the point null hypothesis can actually be a really good enough approximation to allow base factors and so on to do the job just by assuming point null.
Yeah, I was just thinking that converting to the Bayesian approach is only going to be an improvement if you've got a rock solid way of calculating the priors, because if you do what Bayesians often do, which is just make up the priors, you can make the results come out any way you like. So do you, as part of this, do you have a method for calculating the probability of a hypothesis?
Well, to go back here, priors has two meanings in Bayes. One is this. As I say in my work, I don't do that.
You don't calculate the priors?
No, I only do this work, the base factors.
So what are the priors?
So what I'm interested in is the probability of the data given the hypothesis. I'm not interested in how strongly you believe in the theories beforehand.
Ah, so you're assuming equal priors?
No. It doesn't matter what, because base factor is the base factor, regardless of what it is. These could be equal or unequal. But the strength of evidence, that base factor is 5, it means no matter what your prior odds were, you're going to multiply it by 5 to get your posterior odds. Someone had an equal prior, so this was 1, well the posterior odds is 5. If it was the fifth, the posterior odds would be 1. This functions in the same way for all people, regardless of the priors. So forget about the priors, and just treat this as a measure of strength of evidence.
But then if the priors were different, that base factor would be wrong.
No. The base factor is always the probability of the data given the hypothesis, independently of prior odds. The independent terms that you can calculate after these.
Well, what I meant by that is that it would be very misleading.
No, it would be completely leading, no matter what prior odds.
I don't understand. That's an equation. So if you have prior odds and you have posterior odds, then you get a certain factor.
Well, no, I calculate this from specifying my hypotheses, which was Rod's point, how to specify hypotheses, and then working out, well, from that, I can work out the probability of the data given my hypotheses. So, this equation tells you the meaning of base factor, but you don't, at least I don't use it in calculating the base factor. I just set up a model of the null hypothesis, or the two hypotheses I want to compare, and calculate the probability of the data given those models. From the axis of probability, that's all I need to do to get a measure of strength of evidence.
Look at the second line. Okay. Solve the equation. If you have posterior odds, which you are going to have at the end of the experiment.
I don't report this in my results section. I don't report that in my results section. I don't use them to calculate anything. I just calculate this. That depends only on what my theory predicts and the data. And I think that is really scientifically relevant to specify what does your theory predict and what is your data. That's what's relevant. Now, what does it mean when I do that? Well, it means if you reach deep into your soul and pulled out a number between 0 and 1 for how much you believed in your theory before you collect the data, that will be your prior odds. The base factor will tell you how much you should change your confidence in your theory in the light of the data. But if someone else reached deep in the soul and got a different number, absolutely fine. They'll use the same base factor to change their confidence.
Forget your soul. Let's go back to the example. You have 5 experiments already conducted, and then those experiments are going to give you prior odds.
Well, I can do, but that was sort of the discussion we had. I don't use that.
No,
Some Bayesians do. Yes. So some Bayesians do use that, like the Pushkin method. I prefer not to, because I think you can get a long way without doing so.
But let's assume that they are already there, they've been published. How can you disregard what has been published?
Oh no, you don't disregard. You don't disregard the evidence of what's published. That can all go into once I've specified a model and what it predicts, I just look at all the evidence that's relevant, pull it together, and see how strongly the model predicts it. That's all I need to do to be my sort of Bayesian.
Yeah, but then you've got a whole new scope of fishing, haven't you? Because if you make HO, if you're allowed to fix HO any way you like, you can make that Bayes factor come out to anything you want.
Yes, well, psychologists have a strong affinity for a null hypothesis that says no difference. So I put that in the fact that
that's been pointed out. There's all sorts of ways of defining what no difference actually is.
Right, now what I'll say about that is the Bayes factor compares two models. In the results the Bayes factor gives you, everything can be publicly specified. It can be put on the table. There's nothing hidden like there is in orthodox statistics. There are no unknowables. So if I specify two models here and you say, no, wait a minute, that predicts, you can't make those predictions because of the results of so and so. Well, let's have a scientific discussion and see if we can make our models better or our theories better. Well, that's just science. Making public your assumptions and your models and your theories and arguing about them, that is science. To me, Bayes is science. So that's not a statistical question, that's a scientific question. If you want to argue with my models, that's fine, but my models are there publicly, explicitly, to be argued about transparently. And you see how I do it. I try and be as simple as possible. So I have dozens of papers published with Bayesian. And when I specify these models, I just want to say in a few lines. I'm trying to make the models really simple. And that's part of saying, if I said my model is, I'm going to predict, my H1 is I'm going to predict exactly this value, which happens to be the value I obtain, and I give no justification for it, you'll come back and you'll say, well, why do you say that? That's the point I made before. This is just some silly variant theory of the general theory that we're interested in. I'm interested in general theory, not this little subordinate, particular post hoc theory. By post hoc, I mean has no rationale for it.
I don't understand. Crucial aspect of Bayes statistics.
Sorry, I'm really conscious of time now. Maybe we can continue the discussion after we finish the presentation, because there's drinks and
drinks.
Yeah, so let's go with discussion, because I thought it's okay, we need to call the person who will start the closing. Thank you very much. Thank you very much.
Yes. No, I used to find data. I provide all the data, so data comes in that's against
Just calculation that runs the probability of the hypothesis versus the probability of the
There was a technical reason why it is.
Yeah, but you've got any problems there.
Specifying H1, I got the distribution. That's strictly forbidden. Well, only Bayesian, so I have to do Bayesian.
So basically you're using parametric statistics.
Yeah, it can be parametric or relative non-parametric, but yeah, I say we do parametric.
I mean, this is maybe a bit of a break for the statistical mathematical
point of view kind of discussion anyway. I'd like to think actually more about the pre-registration and whether you think this is going to somehow spill over others. Yes. I didn't have to look like that. I mean, I'm quite the business of marketing. Only about the Journal of Business and Psychology, when they do the section of the approach. I mean, the way might be quite a more or less gaining that control that yeah. So how would that affect you?
That's why they want to run it this imagine there's a vein in that area, and there's a registered report that comes out once a month. I think that'll carry more evidence than studies that so that means that's and that yeah, what happens if it's a logging base? Then you get a scale by twice. Yes, and
But do we would run to
I think they have to do the same thing. Yeah, I think the next is what the same thing.
Yeah. Exactly. So just get it over and face it over. The other one would look like we didn't buy the station, but it's just because it knows that.
Yeah, and also you could describe the professional station.
That's great. And in the other one, it's just not as attractive.
Let's say anything about
It's very easy.
Well, we potentially some sort of programs, sir. We couldn't do it full as part of us.
No, what I'm saying was that,
Well, because
I'm saying that we got the problem of subjectivity.
And there'd be no reason why we couldn't do
That would be
I'll tell you what we can do. I wouldn't want to. I think that's
part of this could be such
no, we can do it though, because the well hypothesis is
Sorry? That I say.
We would be wasting essentially other graduates.
So now you have
and if you have someone on my biggest concern is that
you want to give me one again?
useful, I mean, relatively.
So that's the back.
I did.
It's not enough. I mean, it's the same for all areas. So it turns out now, lots of people are
just not one shot.
Yeah, quite a lot of people just have a one shot.
You just trace it and then have this side
but then I can suddenly that's it, really promise kind of
you do that because it's just private to you until you do it up and then you would put things up, take them down. Yeah, so it can be a and then whenever there's one So you might want to you might want to do that rather than have what you might decide in your field, I might decide that people aren't really going to do this and this. So you could have a minimum of 5.
Experiments
on the Bayesian one, it doesn't matter what it is, so you can adjust that.
I guess that might be okay as a sort of possible.
That's next to me. That's it. So what you can do is if you do the same information, different head, what it's saying differently, and see what you that's roughly the sort of answer right there. I like how I just can't see but that's not just that. It's not simple.
Acting up like markers that these people don't know what they're doing. So like if people but if your exams require you, then it's a study of how you would get sort of
the thing about because sometimes people which is now being correlation none of the
actual retraction of the
I don't think all the we're not just 1 or 2 or 3. I think that's perhaps 50 an hour.
Well, if you have 9 if the effect exists, even if your core experiment, your core experimentation factors
are biased. The other kind of mathematics is eventually the noise.
Yeah, I think that was in the journal social psychologists. They usually people meant to know that.
About the highest.
Yeah, even that original paper, that's the thing, the lead author was a social psychologist. When he sparked tools and he made it's a blind basically. He's decision theorists. They don't know how social psychologists run experiments. Lead author was social psychologist. He's now, he took down that model. Whereas people who are if the effect isn't there, other people
you can't be so saying like that.
Yeah, I was looking forward to going back reading. I'm an ultrasound
but it might explain
by the screen, yeah. That's kids who get ill a lot more often.
I mean, that's my observation.
Well, slightly. 10 to 5:30. Yeah, that's right. No, exactly. We need to be doing something different. No, I think it's a real crisis. I expect a lot of Next time you get a biology, they don't have to reproduce it.
In some ways it's worse because of the pressure from the
exactly. Performance management is made it even worse.
But at the time, psychologists were
Yeah, yeah. So it's fraud.
Yeah, so I was like,
Well, you got to take psychology, that's what they know. I can run it.
Yes.
I would have done it, but no, I come back on the 29th, so I'm going to visit my wife.
Yeah, but we ask her if she could stay.
I think if you was suggested, so when I get Jenny to University, you was suggested there.
Why are you ranking Jenny?
Martin and Jenny.
So I need to pick Jenny, so Jenny
Martin
is...
and Jenny.
Send me all the both of them. Free year of you or both. And if you eat all these
But maybe because you also other events to invite external speakers, like neuroscience.
And sometimes these for degree speakers are very neuroscience-y, and sometimes for that where they're just because they're massaging there.
Sometimes they come on other days because they are just, so we have Dr. Robinson next Monday, but just because.
But you really should be, I mean, one thing you could do in the situation we've had is, because this is the Thursday, it's canceled, we moved to Monday because we had this. I hate to see that people say, well, I'll do my Thursday obligatory psychology thing, and then miss something like that.
It's losing feathers. Yeah, chicken.
So that's an option.
So guys, so what do you guys do? I mean,
Just study never studying. I work in the
Someone else would do
So are you available to give me
No. Shall we meet at the parking lot?
If you want to continue, I suggest we Sure, yeah, it's certainly workable because I need to clean it. I put them up to keep it. Yeah.
Well,
because normally there would be someone. Is the room being used? No, it's not going to be used. We did like this. Because the room is actually quite busy these days, so the seminars take place from 9 to 5.
Are we just taking this up to the I'm sure I have.
Yeah, that's what we
need a hand?
You got some, sir. I'm going to take it all in one.
Yes, if you
Otherwise you're going to have to do the back row.
Yeah, to the teacher, just leave it there. I can come back.
Yes, that's very good.
I wonder how it goes.
Left.
I can't work with this people, they were really...
Thank you. But we have to
clear.